Hello. Well, I will take a little liberty, introduce myself before we get to the panel. I'm Jeremy Dann, a professor at University of Southern California. I'm in the Greif Center for Entrepreneurial Studies, and I guess I'm here because last year I launched our Green Entrepreneurship course for undergraduates. So we're working on a lot of exciting areas, industry by industry, in recent weeks. So very excited about this. A maxim as a professor is one great way to learn is by teaching. So I hope it's the same for moderating, because this is an area I would love to learn a lot about today. The area of space and how it impacts the environment and opportunities for green business, green entrepreneurship in space is an area I would love to integrate into the course in coming years. So due to technical difficulties, I'm gathering that we are not having one of our panelists join us. So I don't know if we have quite enough questions. So I'm tasking it to the group and our online viewers. We'd love to have a couple extra questions be tossed in at the end. And who knows, I might toss in a dumb question here and there. But it's up to you to come in with our smart questions at the end. So all of our panelists introduce themselves. They'll do it much better than I. We have Hemali Vyas from JPL. We have Lilly, my notes got all messed up, Lilly Thomas from Development Seed, and Brittany Zajic from Planet. So let me pass it down the line and ask you, just even a few years ago, your organizations, your roles, your jobs seemed like the stuff of science fiction. So can you tell us about those science fiction-like roles and organizations, and also some of the key kind of stops along the way, and even some of the surprising stops along the way that might have prepared you for what you do today?
So I'm Hemali from JPL. In regards to your question directly, so my background has been engineering and project management, particularly systems engineering, with focus on a lot of different technologies, a lot of different missions, from Earth communication systems all the way to Mars, or even SphereX and so on. In regards to the last few years, I think my journey has gone through technology development all the way to project management. I've also left JPL for startups for GPS to have it on our cell phones in early 2000, which was very successful. I think that has opened up the doors to using GPS in many other domains, including vegetation and agriculture and stuff like that. So beyond that, I think I also chair the AIAA Economics Committee, and in today's time, with the exponential growth, especially over the last 3-4 years, in the space economy and its utilization for Earth purposes and Earth data and Earth observation and sustainability, I think it plays a pretty big role, and I think the public-private partnership in the long run would be beneficial.
Hi, everyone. My name is Lilly Thomas. I'm a machine learning engineer at Development Seed. And a bit of context on Development Seed before I really explain how I got here. Development Seed is a very small impact-driven organization of data scientists, geospatial engineers, open source developers, and more or less activists and domain experts, actually. And we really work on problems related to high impact areas that are relevant towards achieving the sustainable development goals. So as a machine learning engineer at Development Seed, I work on primarily computer vision problems using geospatial data, so Earth observation data, kind of synonymous with that. And my process of actually, we're more like in the same classes, I think, at the same time at UCLA, studying remote sensing and geospatial information science. Since then, I've worked at a startup that was focused on developing high-resolution land use land cover models to drive targeted water management practices. And then I moved on to Development Seed, where I work on a much larger array of problems using Earth observation data. So I'll pass it on to Brittany.
It should be on.
Hello? Okay. Hi, everyone. My name is Brittany Zajic. I'm here from Planet Labs, PBC. So as Lilly mentioned, started off at UCLA studying geospatial remote sensing. I was interested in it, and then went to a field of studying it in the private sector at NASA, developed for a few years. And then I saw the growing trend of what Earth observation, especially in the private world, is today. And so about 5 years ago, I joined Planet, and ever since I've been working within the social impact to now business development world, in which I largely focus on strategic partnerships and new market development within natural disaster and humanitarian responses. And how I got there, or how this didn't exist a few years ago, ultimately, what drives my motivation and my interest within this world is that Earth observation has existed for decades, even through like the 1960s, but what we're seeing now is truly a revolution in which we are trying to make it more of an everyday use, in an everyday insight, in which we can better aid really large climatic changes around the world. So looking forward to diving into that more.
Oh, those large climatic changes, they don't need any help. They're happening on their own. But we'll talk about the ways we're going to solve that. And a lot of people are familiar with the way that data from satellites, geospatial data, can be used for governments, military, science, large corporations. As a matter of fact, we probably have some people tuning in that have been a part of the LA County Challenge, looking at the trees and pest infestations. But what in your work is actually holding promise for smaller organizations, smaller companies, smaller implementations, even down to the individual operator, farmer level, et cetera? How is it going to change kind of lives and the economy on a smaller scale basis soon?
So being at JPL, which is mostly developing the satellite system, so you definitely get a lot of Earth data from different missions, whether it's NICE or SWAT or SMAP or many other missions. But beyond that, as an agency as a whole, there are definitely studies that are happening at National Academy of Science that just got released on leveraging commercialization for the Earth science data. And as you start looking into that and you see the growth that's happening in the private funding, I think there's a good inflection point of the funding that is increasing on the private side, and the science and information that exists on the public side, that there's definitely a good opportunity to partner for the various aspects, whether it's climate change, whether it's deforestation, whether it's agriculture. So definitely a lot of opportunities to come together on that.
On that question, I actually think there's an overarching statement with respect to what Earth observation data can do, not just on like the small scale level, but generally speaking, Earth observation data is one of the most, if not the most, cost-effective and globally ubiquitous data sets that are available in the developed and developing worlds, and that is really pretty monumental in that it provides a source of information that can be used to measure and track progress towards achieving sustainable development goals, despite where you are, despite the socioeconomic conditions. Of course, there's knowledge sharing and capacity building that has to be made possible to leverage the data to derive those insights. But I think, as an overarching theme, Earth observation data is really just one of the most incredible data sources from a cost standpoint, especially with the consistent open sourcing of satellite data sets that we see happening today. So I'm just going to provide some topic areas that I think would illustrate a picture of how we use Earth observation data, how I use Earth observation data to address problems, starting at even the most small scale, and then how those could be scaled up to larger interest groups or organizations. So, I mean, the most obvious one to me that comes to mind is like small shareholder farms. Earth observation data, specifically multispectral imagery that are equipped with near-infrared or shortwave infrared, red edge, the new planet constellation is equipped with these wavelengths, can be used to directly measure soil moisture, plant health through chlorophyll content, proximity to hydrological networks and the associated water quality, incident solar radiation through satellite-derived elevation and incline maps. So they're all things that are really like paramount variables to consider as a farmer of any scale in terms of your business. Moving on, there's fisheries comes to mind to me. So we are able to derive information for decision making, in that industry by measuring sea level rise, sea surface temperature, proximity and frequency of oil spills in your local area, proximity to debris discharge sites, which are typically river deltas that are in areas with known waste management problems. Those are some of the most prominent expediting mechanisms for debris from land to sea. Harmful algal blooms. These are all things that we can detect utilizing different wavelengths of satellite imagery, different spatial resolutions and temporal resolutions. And then, moving on from that, I think there's a question of how do we ensure, or how do we help our understanding of varying degrees of equitable living standards, and that's something we can also, derive insights from with satellite imagery. This past year, I recently worked on a project with NASA Surveyor, which is a joint interagency unit that is focused on capacity building for different scientific hubs across the world. And this past year, I worked on a project with the hub that's based in the Peruvian Amazon, where they're tasked with two things, one of which was to detect illegal gold mining activity. And one of the artifacts of this illegal activity that's very detrimental from an environmental point of view, but also from a health point of view, is that communities that are most proximal to this illegal activity are typically indigenous communities. And one of the way that this process happens, this gold mining extraction process happens, is it involves the use of mercury, which is a toxic element, to separate gold from other particles. And that mercury is actually deposited back in the soil and makes its way through different water channels. And so these communities are disproportionately affected by that. And we can actually detect and monitor illegal gold mining activity and associated deforestation, as it's one of the main drivers of deforestation, using satellite imagery through different patterns and like tree canopy height differences. These are all measurable from satellite imagery. Last few things. We can track urbanization dynamics, the development of informal settlements, movement of refugee camps, and this allows us to really provide like rapid synoptic guidance on where to direct aid and those kinds of essentially like resource management in the face of natural crises and other crises. And the last thing is essentially we can also use satellite imagery. This is not an exhaustive list, of course, but one other last one I'll mention is that we can measure proximity of population distribution with respect to the electrical grid, right? We can essentially map electrical infrastructure from satellite imagery, detecting different things that are associated with that, whether it's renewable energy infrastructure or otherwise, and correlate that with population density maps and nightlight data. So. As you can see, there's a lot that we can glean from Earth observation data at different scales, whether or not it's local, regional, national, global. Really the opportunities are endless.
Lilly, If I could just take your definition of Earth observation data and throw it on a t-shirt, I would proudly wrap that every day. That was absolutely phenomenal. To Lily's point, there are a limitless amount of use cases that can be done with Earth observation data. And we are actually learning of more every single day. And so, especially for Planet, we offer both a medium resolution, high resolution constellations, and moving forward in all different types of sensors. In the future, that just means that we're categorizing more and more use cases every day. And the amazing way that in which Planet specifically is able to discover some of those new ones every day is through our education and research program. So we have available to anyone in academia access to our PlanetScope imagery, which allows you to utilize an image of the Earth. On average, the statistic is about we have 450 pictures of any place on Earth's landmass. Lilly can correct me if I'm wrong as a user of the imagery, but what that allows you to do is just immense amounts of time series change of what's going on at just about any scale, right? From a single unit of a piece of Earth to a city or to even a nation or larger, in which I'm not even going to try and elaborate on the extensive amount of applications that Lilly just did, because I would not do it justice. But one other thing I would add, in which we're also really, really forward thinking about here at Planet, is also tracking deforestation. And we're able to do that down to the single tree level, and that's really important for, especially in the tropical regions, for all the different people and places that impacts. And so talking about the scale in which how Earth observation data can impact only one person. So thinking, first thing that comes to mind in that is the education research program, which allows a single person interested in utilizing Earth observation data to get started in doing so. But then also down to impacting one person and how that changes their livelihood based off of different access to different assets and resources around the world, whether that's through livelihood of forested regions or agriculture or urban areas as well.
Awesome stuff. I want to back up just a teeny bit. Here's a wild card question that I didn't ask you earlier. But just as you were saying, I thought maybe our audience online and in the place could benefit from a little satellite and observation 101, as in, everyone knows from spy movies and everything else that we take pictures from space, right? And that these are getting down to the more minute levels, as you just mentioned, the single tree level. But in terms of the capabilities and the wavelengths and the chemicals and the emissions, how else is the technology able to sense things? What is that full range of, spectrum, chemicals, et cetera? So Brittany, maybe you could get us started on that and come back this way.
Yeah, so we'll quickly just dive back into some science of the electromagnetic spectrum, in which certain satellites are able to pick up different magnitudes of frequency in which you can see. So I will probably just give very generic, in which we launched the first satellite into space in 1960s. Since then, we've had, since the 1970s, a robust archive of publicly available satellites, most notably for the US, our Landsat program. Landsat has been continuous throughout the 1970s, 80s or so, in which we provide 30-meter spatial resolution imagery in 8 to 12 different wavelengths. Sorry, I look at Lilly because she'll have to correct me on that. But it creates a really, really long archive of what is available to monitor from that space aspect. And now ESA, or the European Space Agency program, has been built up over the past few decades, and then also the private entities have come in since the 2010s. So we're going from publicly available over the past 50 years to privately available over the past 1 to 2 decades. And so what that means for what you can see all different types of things, both to the visible and also, I guess, like SAR and this active passive sensor. I'm not gonna, gosh, I feel like we're back in school. So I will probably pause there in what my actual knowledge is to that, in which we can probably maybe dive into more about the sensor types or whatever comes to mind.
Yeah, I mean, that was a great overview. I think the only things I would add are that, well, if you, just on the active versus passive remote sensing note, what she means by that is essentially there's 2 different modes of collecting Earth observation data. We have active, we have passive. Let's start with passive since that's the most commonly used. Passive remote sensing is essentially where we are just measuring incident solar radiation. The sensor itself is not emitting any electrical impulses. We're just measuring what is strictly radiated by the sun. And then there's active remote sensing where we're actually emitting a pulse and measuring the return on that. So they are used for different applications. We are with passive remote sensing, we have these different wavelengths. We have the visible part of the electromagnetic spectrum. What we see red, green, there we go. Red, green, blue. Those are, what we nominally think of when we think of, our human visual cortex. But that's what we call visible band imagery. Then you have optical imagery, which actually includes the near infrared, and the near infrared is very useful for measuring temperature. Then you have a whole host of other spectral wavelengths that start to get wrapped into this notion of what is multispectral imaging, and then hyperspectral imaging. The more you graduate, the finer the wavelength ranges are independently, but you have more variety. So you can leverage more wavelengths to pick up the signature of more things on the surface of the Earth. Every single material that is constituting the surface of the planet has a unique spectral signature. So getting it, the more granular the spectral resolution, so the more wavelengths you have, the more materials you can feasibly detect. That is, and then before moving to spatial resolution, we have, of course, active remote sensing, which is really what we use when we need to get past atmospheric obstacles such as clouds, right? Passive remote sensing cannot penetrate cloud cover. So obviously areas that are susceptible to yearly significant cloud coverage yearly, we need some other instrumentation to be able to see through that. We have options for using a radar remote sensing approach. Radar is nominally the active remote sensing type that you would hear of in this domain. And that's able to penetrate cloud cover, and it's also able to capture measurements despite the time of day. Obviously, passive remote sensing requires solar radiation, so the imagery has to be captured during daytime. Radar imagery can be captured any time of day and during any weather conditions. There's one key trade-off that we have to address constantly in this field of work, and that is the trade-off between spatial, spectral, and temporal resolution. So spatial resolution is essentially the unit is based on the unit of area that a pixel represents. So she mentioned that planet imagery is as high resolution as 1 pixel being 50 centimeters by 50 centimeters, and then moderate resolution of 3 meters by 3 meters, and then Landsat we think of as bridging between medium to low resolution, spatial resolution imagery at 30 meters squared. So that is, and nominally there's always been a trade-off between having a fine enough spatial resolution and a spectral resolution, because each spectral channel has to absorb enough light to actually create a signal, and due to sensor requirements and limitations, that there's always been a trade-off between the sheer amount of light that can be received in each spectral channel for a given spatial resolution. And of course, there is nominally a trade-off between spatial resolution and temporal resolution, in that in order to have a high revisit time for any given place on the planet, you would normally have to have a satellite operating at a very high altitude relative to the surface of the Earth, so that it can actually revisit a spot, more frequently, due to just the sheer, dynamics of a Earth orbiting satellite. The way we can get past that nowadays is through, instead of having one singular, sensor on one platform collecting imagery of the planet every single day, we can actually, let's take the barrier of having one unit to having a constellation of low Earth orbiting satellites that are actually able to achieve a very high spatial resolution because they are operating close to the surface of the Earth. But since they're operating asynchronously and spread across the surface of the Earth, you're able to kind of get this marrying of spatial and temporal resolution that we really could not do before small satellite imagery was kind of brought onto the scene.
So going back to that, and I think we've been talking a lot about Earth data and Earth observation data. What we cannot forget about, and linking back to your question of how can it contribute to the other members, you can't have a downstream of data without having an upstream. So I think you have to think about the components that go into building your satellites, whether you're building a CubeSat or smallsat or nanosats, that all form these constellations. And from there, you can think about, there are companies that are.
In studying for this, I learned about the size of what these small satellites are and the range of these. If you could explain that a little bit.
So the CubeSats are like the one I forgot the exact dimension of it, but they're like really small box-like. The small sat is somewhere
About
on
the size of a bread box.
Yeah.
3U.
Yeah, 3U, yeah. And then I think 27U is where they want to get to, but I don't think they're there yet. And then small sats are really somewhere on a few hundred kilograms, and large missions are really like you're talking about 800, 900 kilograms. You're talking about bigger missions over there. And I think what has just opened up in terms of allowing this kind of data, there's a lot of things that has opened up. Cheaper launch access, right, with a lot of new rocket companies that are out there that allows you for cheaper launches, allows you for a cheaper payload to that, because I think to do this Earth observation data, you need a lot of CapEx, a lot of investment funding to build those satellites, which are not cheap. There's a lot of risk that goes in it. And so the fact that you have SpaceX and Rocket Lab and all of these companies that are allowing you a cheaper access to the space allows us the opportunity to have the communication links like Starlinks, allows us an opportunity to put, what Planet has, which I just found out you're like 23 or 24% of overall constellation, which was very interesting. So I think you have to think about in terms of how these constellations are built. There's a lot that goes into it. How can you miniaturize your detectors? How can you make your antennas, like remote sensing she mentioned about radar? How can you make your antennas that are lighter so that you have lesser mass to put multiple satellites on there? So I think every time we think about Earth observation data, there's definitely the data processing and data products and AI and ML that comes to it. But I think for opportunities, others should think about the upstream of it, of how do you build these satellites and what are the detectors and how can you improve them? How can you improve the processing power and the processors that go on it? And are there opportunities to take commercial processors that are rad-hard certified and so that you can use up there? So you got to think from a whole end-to-end perspective of how this industry would open up. And they both play a role into this whole Earth observation data and sustainability and so on.
That's great stuff. And you might have answered part of the next question, which is, what are you and others in your field trying to solve for right now? We have these areas of technological innovation where all of a sudden there's an impediment that we as individual organizations or that we hope other players in an industry or government are helping us overcome. So what are some of these barriers that you're still trying to solve for? And therefore, once they get solved, what new capabilities can we start to see maybe over the next few years from this field? So,
Yeah, okay. The first barrier, the traditional companies. That's an interesting question. I think as an organization, NASA, JPL, I think there is a recognition that there is a need of this partnership. So I think in terms of barriers that we could help solve in the long run is to identify how do you partner, how do you improve the acquisition strategies, how do you come up with better interoperability as you go on. And I was just telling someone this example. If you had multiple cell phone companies that never spoke with each other, we couldn't communicate with each other. So at some point, we'll need to identify some interoperability standards as we develop more public and private. I think government agencies would need to understand a better approach to acquisition strategies so that there's faster bringing in on your startup companies. There is also NASA and JPL, and they already do SBIR kind of contracts that gives private companies enough funding without any equity taking away so that there is a development of those fund projects. So there's a lot of things already going on, but there's a lot more that could play in the role. And I think in general, what is this hybrid architecture going to look like? I don't think we know it clearly. I think there's work to be done, or where does private play a role, and where does public play a role? And so I think there's work that needs to be done on that end.
What comes to mind to me as an ML engineer, working with this data every single day is, first and foremost, data heterogeneity. Most of the sensor products that we use have different calibration approaches, processed in a different way fundamentally. Of course, they may have nominally the same wavelengths or the same bands, but those ranges might be different. So there's so many different artifacts that you have to account for when you ingest data, maybe from different sensors, and usually sensor fusion is required because rarely do you find one data set from one sensor that's complete for all of your needs or your parameters that you'd like to fit into your modeling. So that's one thing that we really have to, even within like inter-data set heterogeneity is something that I encounter quite a bit. And these are almost unavoidable artifacts introduced just from different lighting affects during different times of day, seasonal differences, so you have to deseasonalize your data. Weather conditions, like so many external factors that you have to sort of like denoise from the signal that you're trying to achieve, that you're trying to target. These are all things that it's almost, at this current time, it's very hard to expect your data to come in, like when you're inferencing with your model. For those, since this is an AI room, I can say things like, inferencing with your model. You can't really expect in this real world that the distribution of your test data is always going to be almost, exactly what you have represented in your training data. And then, that transitions nicely into another dilemma that I feel like I encounter quite a bit, which is actually with respect to supervised data, having access to quality supervised data for a variety of different topic areas. Even when there is supervised data, which we use to train our models, our supervised models, there's always some level, depending on how that data was curated and created. There might be human error that's involved in that. There might be class imbalance that's needs to be accounted for. There are ways that we kind of try and do that, amend for that from a programmatic point of view, whether that's through augmentation of your data strategically, or using, I think I heard in the last panel, something about developing training data through a generative approach. So, generative adversarial networks to artificially create samples of real world phenomena. And then there's, these novel transformer approaches that relate to the self-supervised learning mechanism, where you're essentially like using, attending to certain areas, certain subsets of data, and forcing the model to essentially learn features features that relate to another subset of the data by virtue of sheerly what is known in that other subset. So it's a form of regularization in a simplified concept, but still, I mean, these are incomplete solutions and all have to be used together. And I think really this creates a form of a bottleneck in that we have to do so much consideration when we ingest the data. And or nowadays, like the types of algorithms that I'm using, they are neural networks. And of course, when we think of neural networks, we think of robust feature extraction. We think of not having to do that upfront feature extraction, actually, and allowing the model to learn these abstract relationships using convolutional layers. And even so, I think we really, there's still a very intentional way of deciding the inputs to the model, and then really, like, I think iterating on the model. And there's no guidelines for hyperparameter optimization in this space. So I think there's just a constant learning, and still just so much room for experimentation. Yeah. How about you?
So as a member of my business development team, I actually get to wake up and think about this question every day. And so it's really exciting from my perspective to be able to approach and help solve this, because ultimately this leads to solving for new market opportunities. And so I actually turn this into a positive in which we want to continue leading the market. And how do we do that? And so we do that through advancing new strategic partnerships with entities that are interested in leveraging our data in a way that maybe hasn't been done before. And then also entering new markets in which we see a need or a fit for this geospatial Earth observation data, but it's not being done or leveraged today. So it's a really exciting opportunity in which you have to try and solve for what that's going to look like tomorrow and how to implement it. And so it's kind of introducing a new idea to a new space. So it's a really exciting question that is constantly a challenge, but is also what makes the job so fun.
Awesome. Well, now comes the homework portion, because I gave our panel a little bit of homework to look into each other's companies and organizations and pose a question to one of the other panelists. So let's see. Brittany, since you have the mic, can you ask Lilly the question you wanted to ask her?
Yeah, so I think throughout our conversation today, we did kind of highlight just now a lot of the challenges in which we are talking about applying AI and machine learning to Earth observation data. So you talked about a lot of the specifics in which your day-to-day work does that. But I guess to that end, is there anything, if you scale that into like just the larger realm of applying AI machine learning to the analysis of Earth observation data, is there anything larger that comes to mind?
And by the way, team, just to keep on the schedule for the conference, probably about 1 minute-ish for these answers.
Yeah.
I'll do my best. I think so. Actually, with my initial answer to that, I think I actually just went through. So I think one of the last barriers of entry into the field is that these computer vision problems require quite powerful computing resources. And just a couple of years ago, we couldn't do this on our local machines, right? We couldn't, like what? Oh,
Hold it at the top.
Okay, I missed that one. We couldn't train, these computer vision models on our local machines. We had to have access to a graphics processing unit that was like local, somewhere in a data center, and that's expensive. So. One of the revolutions that I've seen is public access to these computing resources to actually use this open source code that is essentially constituting what is a machine learning algorithm that we use with our Earth observation data. So you think of Google Colab is the one that comes to mind for me, and that's been a monumental tool in a capacity building sense, like actually building tutorials for others to use for their particular domain specific problems. And giving them, these tutorials that they can actually, I know they can feasibly run these using Google Colab as a backend. That is still, of course, you think of that, you think of Colab, and we all know that like in the free tier, there's constraints on time and resource applications, and so I'm hoping that will evolve over time. I'm also hoping that like simplified data access interfaces and APIs will make access to Earth observation data, a bit more streamlined, because right now there are so many different APIs and wrappers for access to data archives. And just standardization of data, metadata catalogs and stuff. And there's stuff being done in the stack world, which I won't get into for the sake of time today, but there are movements towards that, but a lot of room still today.
Excellent. So let's see, I'm looking at my list again. So Lilly, if you could ask Hemali the question you have for her.
Yeah, related to that actually. I'm just curious, I work with a team at NASA called the Interagency Advanced Concepts and Implementation Team, but I'm pretty, I don't know at large about how NASA is, given that you guys are, at the helm of Earth observation data, what are you seeing in terms of convergence around standardization of data archive, data catalog, metadata, and also just like simply like program specifications, code structures. Like, do you see a convergence around a set of like open standards? Is my question.
So that's a good question. In the long run, I want to say the answer is yes. In the short run, I'm not sure. That's like a homework question I should take home. But I'm guessing, as NASA is becoming more aware of the private role and the commercialization role, and in general, I was referring to the National Academy study, which was a group of NASA and Space Force and Air Force and all of the different key stakeholders. I think standardization and interoperability was one of the things that they identified. So I'm hoping that in the long run, not only just NASA as a whole, but different government agencies and private companies come together to work on those operability standards.
Now, real quickly, you're about to ask a question, but interesting, last night in my corporate entrepreneurship class, which also covers innovation in other types of organizations, I had essentially the technical head of the the Academy of Motion Pictures Arts and Sciences. And he was talking, and this is a group that helps set industry standards for a very visual medium, obviously motion pictures. And they had all kinds of different data compliance, data standards, metadata, labeling issues. And what you described, I might do a little matchmaking here, because they just did a huge 9-year project where they had, like, literally they said 1,000 different types of files that different effects organizations, sounds organizations, and others were using. I'm wondering if some of the learnings could maybe affect some stuff here. So Hemali, now you have a question for our other panelist.
I think it was more for Brittany, but going back to the standard, like if you look at currently, there's already some standards that apply to the old school missions, right? There's CCSDS standards of how you send your data and how do you wrap it up and what are the metadatas and your error correcting codes and all that falls into it. I just think in the longer run, there needs to be a much more wider stream of participants to come up with a much more larger interoperability problem that we're going to have to solve. So, so Brittany, in the again with this whole private and public and so on, and Planet has played such a big role. Do you see, especially as I'm looking at COP26 and the focus on climate change, and there's a lot of rise of international participation in the satellite data and climate change and so on. Do you see ITAR or some competitive advantage of a company to be any kind of a constraint in coming together to solve this common goal?
So I think just for a quick reference, ITAR is things talking about like international compliance standards. And so in my personal opinion, no. I actually see it's a truly unique innovative and collaborative industry for the Earth observation community. Kind of small but mighty, and has grown interest in the growing years. And so, just to speak personally to Planet, 5 years ago I was like there was less than 200 of us. Now there's over 700 today, and we are all oriented around socially oriented missions in which we're really trying to use space to help life on Earth. And so what I think allows that large mission of trying to help for climate change sustainability is that you get a really passionate community of workers from around the world that come together to try and help with these types of problems. I think one of the most exciting things in the Earth observation community is that, not to sound too cliche, but you can quite literally see the differences. You can see the changing ice, you can see the changing forest, you can see the changing landscapes. And so that visual observation alone tells a really powerful story. And so the community internationally abound that wants to come together to help solve this, and especially going forward with the momentum that was built at COP26, only gives me but positive optimism in the space that we can kind of create together and come together to be able to help solve that within the community and not competitively or independently.
Thank you. Given just a few minutes we have left, we'll entertain some questions. I thought we might see if anyone in the studio audience had a question first. It might work best, given limited time, if it's directed toward maybe one of the panelists. Any questions in the studio audience? Okay, yes. I'll run out. I'll do that move. Your name and what do you do?
No. I live my life well. So a few years ago, back in, I don't know, like say 2017 or 18, given LA is, entertainment industry, which includes gaming these days, there was a NASA talk that they gave on imagery and basically data capture. And the person who was talking was a astrophysicist, and he was talking about how they were exploring capturing data for other planets. And so, for instance, his job was to try to figure out what's below all that ice on some of the planets that are covered in ice. So one of the things that we were exploring in the conversation was whether to use echolation, sound capture, or to use interference beams like in holographic photography, where you have, let's say, a constellation of satellites set up and they're all taking data, visible data, through a spectrum, and then of course the beams of the information that they're gathering intersect, and so then you get a kind of a more than a 3D model of the image capture. So my question is, in your research and in your career so far, or just your own personal interests, do you see our next step as far as data capture, whether it's through visible or invisible sources, which is more efficient, which is higher resolution?
Yeah, so started with multispectral visible because that is kind of the technology that has existed thus far and has worked the best. But no doubt we are moving towards more sensors that capture more of the invisible as well. And we're doing that most notably done through Carbon Mapper, which if you want to talk about, in that we're able to capture all the different types of environments that we want to measure on Earth. And to speak to that, then how that applies to the planetary science sense is that what we know first on Earth and what we study on Earth can then be applied to future planets and missions as well.
And I think it's not what is better, it is what you're trying to study and when are you trying to study and what are your constraints. So I think remote sensing, if you're trying to do something that needs to go through clouds, you're not going to use some visible sensors over there. And in terms of cross-planetary, at some point, we're not there yet, but you're already using some of these spectral images for deep planetary missions also. And I'm sure we'll learn what we're learning from here as we start getting into more astrophysics type of missions to go beyond on exoplanets and stuff. We'll probably apply a lot of these things. And we're applying that to ice giants and how to study that, so yeah.
I would say the last thing on that is it may be less about what is the next sensor product and more about how do you fuse different sensor products to achieve your target objective, right? So you might leverage LiDAR, which is a form of active remote sensing that essentially, is a very high spatial resolution, very dense data set to model variances in essentially elevation, texture. And you might fuse that with maybe not satellite, but maybe aerial visible or multispectral data, and combine the features you're able to obtain from either of those data sets to create a more holistic representation of that target that's on the surface of the Earth. So it's not necessarily about creating a new product, but intelligently fusing existing technologies.
Okay, now we have a question from our non-studio audience.
Oh, okay, thank you. All right. How has remote sensing helped carbon emission tracking? What potential do you see in the future? I know you shared a little bit, but could you expand?
So we really, really interesting projects existing today in which we're able to track carbon emissions through carbon sequestration, through the combination of LiDAR, which Lilly just mentioned, and PlanetScope imagery can be applied with other satellites as well. So that's a really important indice that we don't talk about enough, in which we're starting to measure carbon emissions. Another really important greenhouse gas to monitor is methane. And so methane is a slightly different sensor than the kind of things we've been talking today, but is also something that we're going to be able to track in the next few years. So that's going to pinpoint point sources for methane emissions, and that's going to be pretty. That's a game changer.
Methane is not trackable now via satellites?
Methane is a gas. Not with the current planets. Mm-hmm. Yeah, you need thank you.
You need hyperspectral imager for that. And right. And it's not that it's not trackable. I'm sure they have localized, probably air balloons or whatever with some. Yeah.
But
but
it's
in
a
the
different
past,
type
I would
of,
say it would be more localized. And
I'm mostly speaking to like this satellite imagery that I know best, which is Planet, in which you're tracking a greenhouse gas is different than the type of work that was being done of capturing the carbon sequestration projects, and then also methane being on the slightly different higher spectrum of the electromagnetic spectrum needs hyperspectral. And so, yes, several missions are coming out for being able to better track methane point emissions, and then so together those two things will be able to capture or better monitor both carbon and methane.
so what I'd like to add to that is that it's not that hyperspectral imagers are a new thing. They have existed. They've existed for planetary missions. I think this is a perfect example of when it's a new thing where there's new development, new physics or whatever. This is where the government agencies come in and invest in there. Now is a time to transition where the commercial companies can take over with low cost and higher volume production. So that is where the private part starts coming in, and it's a really great interface to think that way.
Well, you want to do one more question? Okay, one more question.
All right, this is an interesting question. What are the computational bottlenecks arising from analyzing such large geospatial data sets at such high resolution? How do you deal with these challenges?
If I may. So that is an open research question, and always will be, I think. So of course, like satellite data comes into so many different formats and specifications, and different, pixel sizes, and so when we think of satellite images, though, we think of big data, and any given scene or frame, as we colloquially call them, can be typically like on the order of like hundreds of kilometers some scales, and then maybe as fine as like a 10 meters by 10 meters squared. So given that, so when we think of working with like these larger satellite images, we have, perhaps we're working with like a single graphics processing unit. And these networks that we deploy using, these GPUs are, they have, a massive amount of parameters typically on average. Right now, the networks that we use have, millions of parameters. And each of these parameters, generally speaking, have to be trained and optimized, right? So there's a lot that goes into propagating a machine learning network that's leveraging satellite data. So we feed our data into, part of the pre-processing that we do on the data before it actually, gets trained on is essentially breaking down the data into smaller subcomponents. So we call it tiling the satellite imagery. We break it down into like smaller windows of the original scene, and these individual, not even touching the bottom, these individual like tiles get compiled into batches, and these batches are fed to the model sequentially. And essentially, right, after all of the batches have been trained by the model, we have an epoch, and we iterate through epochs. And that's how we manage the size of this data from a computational standpoint. At least that's one of the things that we do.
Okay, well, one thing I learned is that it is possible to learn through moderating. This is a great panel. Much appreciation for our panelists. Thank you very much. And to Todd and the organization for the opportunity here. Thank you.